Hi folks, we're going to continue on with our Unit 6 lessons, and we'll go to number 9. I'm going to give you some time to work on this graph. So here they're asking you to sketch the graph of y equals root x sine x. So again, what I want you to think about is, what is the domain of this function? Here we have the product of two functions, so finding the x-intercepts is easy, okay? And think about what other important aspects of sine x in particular that we used in previous examples to help us figure out what the shape of this graph is going to be. Okay, now just one thing I want you to be careful of is the scale that you use. Is that here we normally graph something like root x, going up by integer values, but that's really not too conducive for sine x. So I would almost say probably better to choose your scale so that it works well for sine x, and then from there, deal with having to work with root x using those choices for scales. Okay, so take about 8-9 minutes to graph this function. All right, so let's take a look at this, and you'll see that I've already started setting up my graph here. Now you'll notice I put my y-axis right at the end because I know that the domain is just going to be x greater than or equal to 0, so no need for any negative values. Okay, and I know that I'm going to have x-intercepts whenever root x is 0, so that happens at 0, and whenever sine x is equal to 0. And so here you're seeing my choice of my scale, and since sine x is equal to 0 at 0, it's already included, but when am I going to have zeros? Well, I'm going to have them at 0, at pi, at 2 pi, at 3 pi, etc. Okay? And the other thing that I know is that sine x lives between 1 and negative 1. Okay? So at the very most, this expression here for any x value is going to have the value that root x has. Okay? Because otherwise I'm multiplying sine, so when it's positive, by some fraction. Okay, less than 1, so it's going to be less than root x. Or when sine x is negative, I know the smallest possible value it can have is negative 1. So at the very least, this function is going to have the value of negative root x. Okay, so let's say it's negative 0.5 that sine x is equal to. Well, then it's going to be above negative 1. But when sine x is exactly equal to 1, it's going to be exactly equal to root x. Okay, so these are the pieces of information that I'm going to use. So notice here what I graphed was root x at the top and negative root x at the bottom, because this function can never be larger than root x and never be lower than negative root x. And I know at certain points they will be equal. Okay, so this essentially creates a boundary for my function. Okay, now the other thing I know is the sign. So root x is always positive. I don't have to worry about that one. But since I'm multiplying them, I realize, between 0 and pi it's positive, between pi and 2 pi it's negative, and so on and so forth. So I know this is going to alternate from positive to negative, positive to negative. But as root x is getting bigger, that value I'm multiplying by to sine is going to be getting bigger. And at some point, sine x is equal to 1. So it's going to be sort of growing. Our peaks and our valleys are going to be growing or decreasing along with root x. Okay? So I know that at pi over 2, they're going to have the same value. At 3 pi over 2, it's going to be the negative of root x, because that's equal to negative 1. So I can add these points to my structure here. Okay? And let's start graphing here. Okay, so I know that it's going to be positive on this side, and and by the way, let's also put in our zeros. So we know it's going to be equal to 0 at 0 pi, 2 pi, 3 pi, 4 pi, and now I think I have enough structure to graph. So I know it's going to, sort of come up. It's going to have to touch that point. Then at some point, it's got to come back down. I know at some point it's going to touch at 3 pi over 2, but then it's got to come back up to 0. And then it's got to at some point touch that value and then come back down to 3 pi. And we start to see the way it sort of snakes up and down a little more each time. but it's always going to be bounded by root x on the top and negative root x on the bottom. So here we see that by using the information we know about both functions, in this case here especially sine x, okay, that it's bounded by -1 and 1, told us that root x and negative root x would be an upper and lower bound to the function, and using the zeros, using when this is at a max of 1, min of 1, we're able to get a decent graph. And again, you can put that into Desmos and check that that works out. Okay, I'm going to leave number 10 as a problem for you folks to work on if you need some extra practice. It's a nice little problem, not too difficult. But now what I want to move to is our next and last combination of functions. And this one here, we separate it out because it's a very different way of combining functions. Okay, so here we have, read the little story here about the oil spill and the way that the oil is growing in the water and the efforts to counteract the effects of the oil. So read through this. You should definitely get to the end of question 11. I'll give you maybe, again, 8 to 10 minutes to work on that. Okay, and try to think when you get to this part here, can you sort of figure out what I'm trying to get at in terms of how we're going to combine two different functions. Okay, so I'll leave you to work on that. All right, so let's have a look at this here. So we've got this tanker that collides with a reef, creates an oil spill. Okay, and here they're giving you some little hints. They're telling you that the oil radiates in all directions. Now, while that doesn't necessarily mean it has to be circular, the implication here is that this oil spill is going to be circular and it's going to be growing over time. Okay, obviously that's likely not going to be the exact case. Depending on the currents, depending on the whatever land is nearby, likely it wouldn't be a perfect circle, but we'll assume that, especially given the questions that are being asked. Okay, when we're asked for the perimeter of the barrier, and then eventually you're being asked for the area of the oil spill. Okay, so we'll assume that it's a circle, and here we see that the radius is increasing with respect to time. Okay. And the first thing they asked us to do is to determine what perimeter you would need to create a barrier around the oil spill if it can be ready in 2.5 hours. And of course, you know that perimeter is a function of the radius. All right. So in order to find the perimeter, we need the radius. However, the radius itself is not a fixed number. The radius itself is changing. We've got the radius, which is a function of time. Okay. So one way you can solve this is determine the radius at time 2.5. Okay, so 2.5 over 2.5 plus 1. So let's calculate that. Okay, so 2.5 divided by 2.5 plus 1. Okay, it's about 0.71. Okay, and I can't, radius, does it tell us T in hours? Oh, kilometers, there we go, 0.71 kilometers, so quite a big oil spill. And then once we have this, we can now plug this into our perimeter function. And of course, the perimeter for a circle is 2 pi times the radius, so 0.71. Let's calculate that, so times 2 times pi, and we get about 0.49, I guess, kilometers. Okay, so very reasonable. And then the next step, plane will fly over to release the dispersant. What area will the dispersant have to cover? So here, presumably, that barrier has held, so the radius has not increased. So again, we know that the area of a circle is also a function of the radius. Okay, but because we've now found the radius given the time, we can find the area that we have to cover. So pi times 0.71 squared. And then here, what does that give us? Pi times 0.71 squared. Okay, about 1.58. square kilometers. Okay, so nothing really interesting or complex in this problem in terms of solving it. Okay, but if you had to do these types of calculations over and over again, okay, you might be encouraged to instead see if you can find a relationship between perimeter or area directly with respect to time, okay, and not have to go through this process of first determining a radius, then inputting it into another function, okay, is we want the output of this radius function to go into this perimeter and then area function, but can we do it directly working with time? Okay, so here, this is where you realize that the circumference is, of course, a function of the radius, but the radius itself is a function of time. And what we're doing is we're taking the time value, putting it into the radius function, and then the output of that function becomes the input to the next function. Okay, so can we just find a formula that takes us directly from time to circumference? So here, let's see what happens where I replace my radius function by whatever formula is given. And of course, using our knowledge of function notation, we can now just input this whole thing into our circumference function. Okay, so we'll write that as 2 pi t over t plus 1. And so now we can do this calculation in one step. Given the time, we now have a formula to calculate the circumference of this circle. But of course, we have to remember that there was that intermediary piece of information of how the radius increased with respect to time. Okay, and again, similarly, we can write a formula for area with respect to time. Okay, and of course we do that using this intermediary of the radius, that the area we know as a function of radius. We know now the radius is a function of time. And so as we did before, okay, and then now we've got a formula for area directly in terms of time. Okay, so this is going to lead us to our last way of combining functions. And before we get to defining it officially, I want you to think about how we have actually seen this before. So while this is a completely new way of defining a combination of functions, it's actually something we have done in the past. So I want you to take a couple of minutes and see where we've seen this before, where the output of one function becomes the input to the next function. All right, take 2 minutes to talk about that. All right, so I hope everybody recognized that we'd seen this before, and of course we saw it when we worked with inverse functions, okay? That if I take an input and input it into some function, then the output of function f, if we now input that into its inverse function, so the output of f now becomes the input to f inverse, we saw had a very special property that it just outputs the original input. Okay, and we can do it the other direction. We could start with f inverse of x, and if that output becomes the input to the function f at x, yet again, we get back to the original input. Okay, so this idea of combining functions where the output of one function becomes the input to the other. Okay, but what's very important to understand is this is not a combination that necessarily involves multiplying two functions, dividing two functions, adding two functions, subtracting two functions. It's not an operation between the y values of the functions. It's like a two-step process. Your input goes into one function, and then that output gets input into the next function to produce this new output. Okay, so let's now take a look at the definition for this combination, and this is what we call the composition of two functions. Okay, so composition of two functions, and notice the notation here, it's this little open circle. Okay, so do not mistake that for a multiplication. So make sure when you're drawing it, you're not drawing it as just a dot. Just a dot, a closed dot, represents a multiplication. Here, that open circle represents the composition. And our definition for this new function, it's defined as f of g at x. That's how we say it, f at g of x. Okay, and as we see, we always go from inside out. You have an input that goes into one function, and then the output of this function becomes the input to the next function. All right, so we're going to start to ask ourselves a lot of the same questions as we did before. In fact, if you remember, the first question we asked about our other um, um, combinations was, is this a commutative operation? So is f circle g? So we can say f composed with g, but very often we just say f circle g. Is f circle g going to give you the same output as g circle f? So that's one of the things that you're going to look at a little later on. And of course, we're going to be interested in the domain of this function. What inputs are even allowed? Okay, will it be the same thing that it needs to be in both domains? All right, so you're going to take a look at that. But for now, I want you to try to apply this definition to these examples here. Okay, now be careful. We cannot assume that these two will give us the exact same answer. You're going to have to go through the process of checking it out and see if we can say something about the commutativity of the composition of two functions. Okay, so just go along. I'm going to ask you to get to at least f, okay? But if you think you have a good conjecture as to how to find the domain of f circle g, you can go on to do part g here, okay? But we'll give you about 6-7 minutes to work from A to F. All right, we'll see you in a bit. All right, so let's get back into this here. All right, so we've defined these functions f, which is x squared minus 4, and g, which is root x. And the first thing they're asking us to do is determine f circle g at 4. So I'm just going to apply the definition. So here, this would be the same as f of g at 4. And as we talked about, you always go from inside out. So what is g at 4? Well, g at 4 is just the square root of 4, which is 2. So now the output of g at 4 is going to become the input to f. And here, 2 squared minus 4 is just 0. Okay, so now here I'm asking you to determine g circle f at 4. So if these two expressions are the same, then it might, give us the idea that perhaps composition is commutative. But if they're different, then we know for sure it can't be commutative. Because remember, in order for something to be a property, it's got to be true all the time. So let's do it here. So I'm going to use my definition. This now becomes g of f at 4. All right, so here f at 4 is 4 squared is 16 minus 4 is 12. And then g at 12 is just the square root of 12. And we could see that this is definitely not equal to 0. Okay, so here we can say that f circle g is not the same in general as g circle f. Now, notice that it can be true, because if we take our old example of the inverse functions, we see that in this case here it was commutative. Whether I did f circle f inverse or f inverse circle f, I got the same output. But in general, this is not a property of composition, so this is not commutative. All right, so that's good. One out of the way. So here you can keep playing with this here. So you have f of f at 3. Okay, so again, you can take the composition with a function with itself. So what is f at 3? So 3 squared is 9 minus 4 is 5. Okay, and then put 5 into here. 25 minus 4 is 21. Okay, there you go. You can do it. Let's now do g of f at 1. So again, just another quick example here. So let's start with f at 1. So 1 squared minus 4 is negative 3. And now we're going to take g at negative 3, which of course is just the square root of negative 3. And this is where you realize that this does not exist. Okay, so we found a value that's not in the domain of g circle f. Okay. Now keep in mind, when we were adding, subtracting, multiplying, dividing, okay, the rule, the general rule, division had that extra little property, but the general rule was as long as the input was in both domains, then it would be in the domain in the combined function. But let's look here. F at 1, where's F here? F is defined at x equals 1, and G is defined at x equals 1. So we actually made a very big discovery that just being in both domains does not guarantee that it's going to be in the domain of the composition. When you think about it, it's not too surprising because it's not 1 that's being input into the function G, it's F at 1. Okay? So it's not just enough for 1. Let's take a look. Definitely needs to be in the domain of F. Okay, that's a certain condition, because if this number here is not in the domain of F, then the first part of the process can't happen at all. But it seems as though the second condition is not for 1 to be in the domain of G, but for F at 1 to be in the domain of G. Okay, and this is going to give us our, what we presume is going to be our rule for the domain of a composition of functions. So what is the domain of F circle G? Okay. Now I'm kind of asking you for the conjecture, and then, I'm going to ask you to test it out, but I'll give you, I'm going to, just to save ourselves some time, I'm going to say that when we get to the actual rule, it will be the rule that we're writing here. Okay. So you will check these, take some time to check these on your own, but you will find that this is indeed the rule for finding the domain. So what do we figure has to happen? So here, if I'm working with F circle G, let's make sure I'm working with the correct order, because we see the order does matter. So this is the same as F G of X. So what's the first thing that must happen? X must be in the domain of G. Okay, so this is the set of all X's that are in the domain of G, such that that's not enough. It's not enough to just be in the domain of the first function. Okay, remember what we saw. It's not X that needs to be in the domain of the second function. It's G of X, such that G of X is in the domain of F. Okay, so based on what we saw, this seems to be what needs to happen, is you need to be in the domain of the first function, and such that your output is then in the domain of the second function. All right, now something I didn't specify earlier, but this is kind of take this definition just to make sure you're remembering what order. Notice here when I have F circle G at X, the first function that I'm applying is the one closest to the input. That's the first function I apply, and then the second one, which receives the output, is the one that comes first in the order. Okay, so just keep in mind that, make sure you're applying this definition very carefully. All right, so now what I want you to do, and I'm going to suggest that you use a little graph to see if our conjecture is correct. See if you can figure out, and maybe, like I said, use a little graph to help you out. All right, and check with Desmos to see if this indeed does work in giving you a domain. So I'll give you about 5 minutes to work on these two. All right, we're back. So let's take a look here. So I just wrote out these functions. So here, G of X is root X, and then I'm inputting that into F at X. Now this is where you have to be careful, because we know that when we square a square root, we just get X here, okay, minus 4. And when you look just at the end result, you realize, hey, wait a minute. The domain of this end result, once I've simplified, is just all real numbers. But you have to keep in mind that this was actually a two-step process. X first had to go into root X. So we have to specify here that X has to be greater than or equal to 0. Okay, so when you graph this on Desmos, you probably would have seen something that looks like that. Okay, because of course that initial step of not being able to take the square root of a negative number still holds. Okay, so that seems to fit what we say. So now here I did g of f at x. So here f at x is x squared minus 4. And then I'm taking the square root of all of that. And this is where we realize, whatever's inside the square root, okay, needs to be greater than or equal to 0. So in other words, x squared minus 4 needs to be greater than or equal to 0. But this is something you know how to solve. Okay, we saw that we could solve polynomial inequalities by factoring and using the graph of the function. So x plus 2, x minus 2, greater than or equal to 0. And we use our little number line. Okay, here negative 2 and 2. And we know that because this has a positive leading coefficient, it's going to look like that. Okay, so remember what we need is we need the output of x squared minus 4 to be in the domain of g. In other words, we need the output of x squared minus 4 to be greater than or equal to 0. So the only numbers that we can take are those that produce outputs greater than or equal to 0. And so here, the domain would be, x and r, such that, okay, x is less than or equal to negative 2, or x greater than or equal to 2. And of course, I could also use interval notation. Okay, so again, this two-step process. X squared minus 4 can take in any inputs, but these outputs need it to be greater than or equal to 0. And the ones that do that are the x values, the inputs that are less than or equal to negative 2 or greater than or equal to 2. All right, so it looks as though, and again, the graph of g of f at x doesn't look like this. Remember, this is just the graph of x squared minus 4, but you would have likely seen a graph that kind of looks like that. All right, but the important thing was that the domain fits what we established. Okay, so last thing we're going to do for this lesson is to use our examples of a function that's given as a set of ordered pairs, okay, to really kind of make sure we understand how this composition works. So first thing, I'm asking you for the domain of f circle g, g circle f. I would not expect those to be the same. So again, since I'm asking for the domain, I'm asking for a set of numbers. Here, I'm asking you for the actual function g circle f. So I'm expecting you to give me a set of ordered pairs, okay? And lastly, I want you to work on number 15, okay? I want you to apply the composition in both directions, and I want you to simplify as far as you can and see if that tells you something interesting about these two functions, okay? And that's where we're going to stop with this lesson. So I'll give you about 10 minutes to work on this stuff here, and then we'll take it up. All right, so let's take these up here. Okay, so here I want to find the domain of f circle g. So remember that f circle g of x is f of g of x. Okay, so I know that whatever's going to be in my domain of this function has to at first be in the domain of g. So what I'm going to do is I'm going to start by listing the domain of g. Okay, so g here we have -1, we have 0, we have 1, we have 3, we have 5, we have 7, and these are our starting values, okay? Anything that's not in this set can't be in the domain of f circle g because it's not in the domain of the first function we're applying, okay? So what I'm going to do now is I'm going to test each of these. I'm going to look at the output of g and see if it's if it's one of the inputs of f. So when I take g at -1, the output is 0, but 0 is not in the domain of f. So that one can't be included. Let's look at 0. 0, g at 0 is equal to 3, and that output is in the domain of f. So that one's going to stay. Let's look at 1. 1 outputs -3. -3 is not in the domain of f. Gone. Okay. 3 outputs 0. 0 is not in the domain of f. Gone. 5 outputs 4. 4 is not in the domain of f, also gone. 7 outputs 4, as we saw, not in the domain of f. So the only thing that survived, checking the outputs of G as being in the domain of f, the only one that survived was the 0. So there's only one point in this function, okay? And that's the value at 0. Okay, but since I'm only asking for the domain, that's all we have to give. So now let's do the same thing, G circle f. But remember, this is G of f at x. Okay, so I'm going to start with the domain of f. And let's see what that is. Domain of f is -1, 1, 3, 5, 7. Okay, and let's do the same thing. Okay, so f at -1 is 1. 1 is in the domain of G, so that stays. Let's do 1. 1 produces a 4. Okay, 4 is not in the domain of G, so that one's gone. Okay, 3 produces 7. 7 is in the domain of G, so that stays. 5 produces -1. -1 is in the domain of G, so that one stays. And 7 produces 0. 0 is in the domain of G, that one stays. So the domain of G circle F is much larger. Okay, so -1, 3, 5, 7. Okay, and this is the function that I wanted you to determine. So here I'm going to start with these domain values and then determine the outputs. But remember, oh sorry, it's G circle F that I want. What I'm going to be getting here is a set of ordered pairs. All right, so I know my first ordered pair is going to have an x value of -1. So let's see what happens. -1 becomes 1, then 1 becomes -3. So that's the output. Okay, so on the side I'll write it out, is that G of f at -1, f at -1 is equal to 1, and then I calculate G at 1 as an output of -3. Okay, so I'm not going to write all of them out, but this is essentially what I'm doing here. All right, so let's go to the next point. Next point, it's input of 3. Okay, so what happens? 3 outputs 7, then I input that into G. 7 outputs 4. So there you go. There's my next point. Okay, let's do now the 5. Okay, f at 5 is equal to -1, and then G at -1 is equal to 0. Okay, and now the last one is 7. Okay, 7, G at 7 is equal to, sorry, f at 7 is equal to 0, and then I input that into G. G at 0 is equal to 3. Okay, and there you go. There's my function. Okay, so it's about understanding this two-step process to figuring out what the possible domain values are and then determining the actual points in my function. All right, so let's take a quick look at this one here if you had time to do it. So let's just, this is, again, I notice how I always write my definition, so I'm not mistakenly going in the wrong order. So here I've got f of g of x, so this is 1/2 x minus 4. And now I'm going to take this and input it into my function f. So I replace x by 1/2 x minus 4, and then plus 8. And what do we have? 2 times 1/2 is 1. 2 times -4 is -8, plus 8, and lo and behold, look what we get. Okay, so I suspect a lot of you saw this coming. So what is this telling us about the functions f and g? Well, it looks like it's telling us that these two functions are inverses of each other. And let's, make sure, let's put a point on it to make sure that the exact same thing happens when I do f of g of x. Okay, so f of x is 2x plus 8. Let's now input that into the function g. And let's see what happens. Half times 2 is 1, plus half times 8 is 4, minus 4, and there you go, we get x. So this says that f and g are inverses. So this is a way of testing whether two functions are inverses, okay, is to take their composition, and if they just output the same thing that was input, then you know that they're inverses of each other. Okay, that's it for this one.